Today we'll look at buoyancy for submerged bodies. So as you recall, for a floating body, if the density of the object is less than the density of the fluid, then the object floats. But if the density of the object is greater than the density of the fluid, then the object is going to sink. So in this case we have the force of weight being greater than the buoyant force. And therefore the block is going to accelerate downwards. So there's contact forces on the surfaces of the block due to the fluid pressure. So on the top of the block we have a contact force due to the pressure. On the sides the force is going to get larger because the average depth of these surfaces is greater than the depth of the top surface. And at the bottom we're going to have an even higher resultant force. Okay, because the depth of this surface down here is greater than the depth of the other surfaces. And of course if you look in 3D, those forces are going to act in the middle of the surfaces, and you're going to have forces in and out of the plane. Okay, so these forces, this one, this one, this one and this one are equal because the surfaces are at the same depth basically. And buoyancy is the difference between these two vertical forces. Okay, so the net buoyant force is going to act upwards. So in this case you got forces acting on the top and bottom surfaces of the block. So the difference between these forces is the buoyant force, and the buoyant force is going to thereby have a smaller magnitude than the force of weight, as we can see. So therefore the object is going to accelerate downwards, and we can thereby apply Newton's second law in the vertical direction. So the net force in the vertical direction is the mass of the block times the acceleration. And I'm going to take my positive y direction to be downwards. So what we have is the force of weight minus the buoyant force is equal to the mass times acceleration. And as we said, according to Archimedes' principle, the buoyant force is the weight of the displaced fluid. So that will be the density of the fluid by the submerged volume by gravity. And the force of weight is the mass times the gravitational acceleration of the object. So that will be the density of the object by the volume of the object by gravity, and we're subtracting the two. And that's equal to the mass, which is the density of the object, times the volume of the object, times the acceleration. And in this case, the volume of the object is equal to the submerged volume because the object is entirely submerged in the fluid. So therefore we're going to get a cancellation of the volume, and we can solve for the acceleration. Okay, so dividing through by the density of the object, well, what we get is g minus the density of the fluid on the density of the object multiplied by g. So that's equal to the gravitational acceleration by 1 minus the density of the fluid on the density of the object. Okay, so what does this tell us? It tells us that if the density of the fluid is equal to the density of the object, then this term in the brackets disappears, and therefore the acceleration is 0. So this tells us that the object is in static equilibrium, so the object just sits there and hovers and does not sink. Now what if the density of the fluid is less than the density of the object? Well, in this case this term would be less than 1, and therefore the acceleration is positive. So the object is effectively going to sink in this case. But what if the density of the fluid is greater than the density of the object? Well, then this term here is going to be negative, isn't it? Okay, so 1 minus a number larger than 1 is negative, so the acceleration is less than 0. So it's going to act upwards, and the object is just going to float to the surface. And I'll see you in the next video.